Hi, everyone, and welcome to our webinar using ScyllaDB for extreme scale workload. We'll get started in a second. Before we do that, I want to run a quick poll. How often do you scale your database? And that's include both scale out and scale in. In other words, adding machines or removing machine. And let's go for both your NoSQL database and your relational database. Okay, thanks, and we'll collect the answer and share it later. Before we get started, let us quickly introduce ourselves. So my name is Tzach Livyatan. I'm VP Product, working in ScyllaDB for many years. And with me is Attila.
Hi, everybody. Thanks for joining. So my name is Attila Toth. I'm a developer advocate with ScyllaDB. Before that, I worked as a software engineer or a developer advocate in the data space for more than 6 years now. And I live in Budapest, Hungary. Looking forward to the webinar.
Thanks, Attila. What we're going to do today is we're going to split the work between Attila and myself. Attila going to explain what is ScyllaDB, give an introduction to ScyllaDB and ScyllaDB use cases. And maybe do a quick demo of ScyllaDB performance. Then I will deep dive into the design of ScyllaDB, how it was designed and implemented to support high throughput and low latency. And then, as time permits, I will switch to a few features from our roadmap. Some of them already landed in open source. Some of them will soon be landed in open source and enterprise, like tablets. And then we're going to do a quick summary and Q&A. So with that, let me switch to Attila, and I will be back soon after.
Thank you. Let me share my screen. All right. So let's get started with why ScyllaDB. So if you are not familiar with ScyllaDB, ScyllaDB is a NoSQL database that focuses on low latency and high throughput. If we want to put ScyllaDB in the same context as some other similar databases, we could say that ScyllaDB provides the power of Cassandra at the speed of Redis with the usability of DynamoDB. Generally speaking, we provide the best price and performance in the industry. A great benefit of ScyllaDB is that it provides great performance out of the box. So there is not much configuration that you need to do in order to achieve great performance. We are compatible with Cassandra and DynamoDB. So our main API, our main language is the Cassandra query language, but we also have a DynamoDB API. As far as deploying ScyllaDB, what are your options? You can choose between different flavors of ScyllaDB. So you can use the open source version of ScyllaDB, which you can use for free, and you can deploy it anywhere you want to use it. So any cloud or your local machine. We also have ScyllaDB Enterprise if you need additional features and support. And we have our own cloud offering as well, which is ScyllaDB Cloud, if you don't want to manage the ScyllaDB cluster yourself. We have a lot of large customers. You might recognize some of the logos on this screen. I might mention a few of them, like Discord. Discord is a very popular chat messaging app. You probably heard about it. They use ScyllaDB to store trillions of messages. But then we also have companies from other industries, like the streaming industry. We have Disney Plus. We also have some companies from the gaming industry, like Supercell or Epic Games. So a diverse set of companies who need low latency, a low latency database. Now, if you want to put ScyllaDB on the CAP theorem chart, which is, if you're not familiar with the CAP theorem, it's a way to categorize databases based on availability, consistency, and also partition tolerance. And if you want to put ScyllaDB on this chart, we would put it on the availability and partition tolerance side. So what does that mean? It means that ScyllaDB focuses on being highly available and partition tolerant. So what does availability means? For example, if you make a request to the database, will you always get a response? Even if one of the nodes or multiple nodes go down, will you always get a response? If the answer is yes, then that database is highly available. Then partition tolerance, what does that mean? What happens if there is a network failure between the nodes? So there's some kind of connection or messaging issue in the cluster itself between the nodes. Will the database be functional and operational? And in the case of ScyllaDB, the answer is yes to both. So we are on the right side, or on the availability and partition tolerance side of this chart. And as opposed to being consistent. So that's kind of the idea with this categorization, is that you have to choose two between these three factors. Another way to categorize databases is by data model. So if we look at it from this perspective, ScyllaDB would be a wide column store, or you could also say a key value store. But there are also document stores out there, for example, MongoDB. There's also key value stores like Redis, and then graph stores like Neo4j. But there are many other categories that you could come up with nowadays. For example, vector databases, that would be another category as well. Now, the customer, the users who are happy with ScyllaDB, they usually focus on these three things. That's what they care about. So they care about high throughput, which could mean how many requests a database can process per second. They care about low latency. So the latency between the latency, how fast the database can process a request. And then obviously they care about predictable cost. And these are the things that ScyllaDB specializes for. These are the things that ScyllaDB is really good at. ScyllaDB has kind of a ring architecture. As you can see, you can deploy ScyllaDB in different regions across the globe. And then you can have different settings applied to different regions. So for example, you can have the replication factor different for each region. And similarly with consistency as well, ScyllaDB is an eventual consistent database. And similar to replication factors, you can have different consistency level settings per region. So in one region, you can have a consistency level of 1, for example. So you will only need one node to successfully respond to a request. And in another region, you can have a consistency level of local quorum, which would mean that you need the majority of the nodes to respond successfully to a request. Now, one kind of proof that ScyllaDB can survive disasters, and it can stay up and running without issues, is the disaster that happened a few years ago. I'm sure a lot of you have heard about it, when an OVH data center got destroyed by fire, and we actually had a user who deployed ScyllaDB on OVH in that specific data center, and they were able to survive the incident without issues. A few ScyllaDB nodes went down, but the cluster overall was able to be operational and serve requests throughout this whole incident. Another thing I wanted to mention, which might be interesting for some of you, is that ScyllaDB has an internal embedded cache. That is often good enough to replace external caches. So, for example, a lot of people use some database, and then they're not happy with the performance, so they introduce an external cache. But over time, it can become it can cause a lot of headaches because of the complexity of managing multiple technologies, multiple items in your infrastructure. It can also become more expensive. And so we have a lot of customers who went from having an external cache and their main database to just have ScyllaDB as their main database. And they use the internal embedded cache that ScyllaDB has because it's easier, less expensive to manage, but it still provides the performance that our users expect. We have SQL extensions to either enable or disable cache, so you can customize it if you want to. Then, if you want to look at some numbers, generally speaking, ScyllaDB is faster, so it provides higher throughput and lower latency, and less expensive than a lot of the other similar technologies. But we also suggest that first of all, if you want, you can read the benchmarks because we have some third-party benchmarks as well. Obviously, we've wrote benchmarks as well, but you can also do your own benchmark, and we're going to give you just in a second, we're going to show you a tool how you can do your own benchmark so you can test your own workload on ScyllaDB. So let's see some customers and what they were able to achieve by switching to ScyllaDB. So Disney Plus, they went from Redis and Elasticsearch to ScyllaDB, and they were able to lower their latency to under 1 millisecond, and that is P99 latency. So that's pretty impressive. Then I already mentioned Discord. They replaced the Cassandra with ScyllaDB, and they were able to go up in scale, but use fewer nodes. We also have Fanatics, who went from a 55-node Cassandra cluster to just 6 ScyllaDB nodes. Grab, another interesting user, they switched from an external cache Redis to ScyllaDB. Comcast, they went from a huge Cassandra cluster with almost 1,000 nodes to just 78 ScyllaDB nodes. So that's also a big difference. And others, QB, Zillow, Palo Alto. So now the last part of the presentation is a demonstration. So now I'm going to switch over to a graph on a dashboard that is actually ScyllaDB monitoring, part of ScyllaDB Cloud, and I'm going to run. I'm already running actually 1 million operations per second to a 3-node ScyllaDB cluster. So let me switch over to this dashboard. So this kind of dashboard and other useful dashboards are part of the ScyllaDB monitoring stack. And as you can see here, we are running exactly 1 million requests per second using EC2 instances. And what we have is a really good latency. We only have 1 millisecond, so single-digit P99 write latency. If you look at the read latency, P99, that's also just single-digit 2 millisecond, which is really, really good, considering the fact that we have 1 million requests per second. And as you can see on this chart, we are making use of the cache that I mentioned, the internal cache. So basically, all the requests that are being served are using the cache. So that's part of the reason why ScyllaDB is able to provide this kind of performance. So if you want to run a similar demo to this, but maybe with your own schema, with your own workload settings, I suggest that you should check out this GitHub repo that we have, 1 million ops demo, and that has a Terraform project, actually multiple Terraform projects that you can use to spin up a ScyllaDB cluster instance in the cloud. You can either use ScyllaDB Cloud or you can use ScyllaDB Enterprise, in which case you will use your own AWS account to spin up a self-hosted version of ScyllaDB. And then you will need to add your credentials and configure Terraform, and you will be able to run your own benchmarks and see whether you like what ScyllaDB provides. So that's all I wanted to share. I hope it was interesting. And now I'm gonna give the mic back to Tzach.
Thanks, Attila. It was very useful. And just to repeat, the demo that Attila just showed is available for everyone. You are more than welcome to run it and maybe tweak the loaders to match your own workload profile. So I assume you already believe us that Scylla have a very high performance and very low latency, but the question you might ask yourself, how did we get to such a great performance? So of course, I'm not gonna deep dive into each of the items, and it's an ongoing work for more than 10 years to produce a high performance database. I do want to go over a few of the basic principles that many of them would decided when we started the project, how to get to such a high performance and low latency. And if you want to deep dive into each of them, you can read the documentation further or stay for the Q&A. So these are the 6 high-level design architecture decisions that we made to make Scylla faster. The first, maybe the most controversial to some extent, is we decided to implement in C++. Why C++? C++ allow you to have full control of memory and I/O and everything, all the other resources in the machine. Java and other garbage collected language are great, but if you want to keep and control the latency, they are out of the question because they can trigger a garbage collection at any point. Garbage collection can take a few milliseconds or even much more than that. And we'd want to control that. In Scylla, we have a lot of offline and online process, which you can think about them as garbage collection to extent, like compaction and other things, but we want to control them. We want to control when they happen, when they kick in, how much resource we want to allocate to them, etc. So C++ was chosen. The second thing, everything is async. What do I mean by everything async? People here that used to develop with the web, and I'm sure most of you guys know that if you send a request to a server, you usually do it in an async way because the response might take even a second to get back. And in the meantime, you want to do other stuff. So one way to implement that is using threads. You can have multiple threads, and the thread just waiting. There is a context switch and the thread waiting for the next one to take action. That can work, but as I will show later in the next slide, it's not good enough for a database, and also you need huge amount of threads that compete with each other. So usually you use, especially for example in JavaScript, you use async calls. We extended that through a third-party library that we created as well called C-star in C++, to make all the calls async. And by all the call, I mean networking, but also storage and communication between cores and everything else. So there is never like a context which require when you, for example, write or read from disk. And that's a good segue to these slides with the cute puppies. In many systems, mostly when you develop in Java, but you can do it in C++ as well if you want to. The way to overcome latency issue or to overcome a synchronization issue is spawn a lot of threads. There are many threads. Each time you need to go, for example, to a shared memory, they do some kind of async between them. One win, the other wait. If you need to I/O, there is a context switch. But the result of that, and we prove it with profiling, that huge amount of the resources in the machine is both CPU and memory is going for context switching. And actually not as time actually processing and doing what a database should do. In Scylla, we adopted a way of programming development that called shard per core. In this way, you have an actual thread per core pinned to this core. There is never a context switch. Everything is async, as I mentioned earlier. If a thread or a shard need to access I/O, we do it in an async way. If you need to communicate with another core on the same machine, he will send the message. There is never a competition between two threads on the same resources. So if two threads never have to access the same memory. Each thread or each core have its own slice of the memory, its own slice of the networking, and its own slice of the disk. And each of them work as independently as possible between each other. And this is probably the most important design decision we made in Scylla. Unified cache, the one thing I will mention about it is that using page cache is usually a bad idea in databases, and Scylla avoid that. We manage everything on the machine, including the memory. We allocate the RAM between the cache, which is roughly 50%, memtable and other resources, and leave 10% for the OS. But we are not letting the OS manage our memory or caching. And by the way, we avoid a lot of unnecessary system calls as a result, which are pretty slow. I/O scheduler, it's a very interesting feature. So early on, we identified that not all storage or all SSDs are born equal. And by the way, Scylla usually run with SSDs because that's what gives you the best performance. So what we are doing now is when you start a new when you install a new instance of Scylla, we do a quick benchmark on the machine, unless it's a cloud machine, so we already have this benchmark done, but we're doing this quick benchmark on the machine, trying to find the sweet spot of the storage. And the sweet spot means how many concurrent read requests and how many concurrent write requests this SSD can handle before the latency starts spiking up. The SSD have concurrency too. If you send more and more parallel or concurrent requests to the SSD, until some point, the throughput will be better because it can handle all the requests. But at some point, you get a threshold, which is sometimes undocumented. You get to a threshold of the disk. And at this point, the storage start to accumulate your request in a queue. You don't have control on the prioritization of the queue, just the process or the user application just have to wait. And the SSD processes the request one by one and send the response back to the application. Now, we don't like that for two reasons. First, we want to control this queue and control this priority, and we don't want to overload the SSD. So with this scheduler, the I/O scheduler, we have full control of what's going to the disk. More than that, we can leverage the fact that we are controlling the disk and maintain our own priority queue of all resources, including I/O. That means that high priority requests can be processed faster and low priority requests can stay longer in the queue. And through a unique feature we call a workload prioritization, we actually let the user control which workload can be marked or signed as a high priority and which one is low priority. You can actually assign what we call shares to each workload. So you can say, hey, this is a real-time process. Latency is super critical to me for this workload. I want to give it a lot of shares. This one is an analytic workload. I don't care as much if the latency is above 1 millisecond or even above 10 milliseconds, as long as it doesn't hurt the real-time request. So you can actually assign such workload prioritization for each workload, and this use under the hood the IO scheduler that I mentioned earlier. So this was a really summarize of how Scylla was created for high performance. The next topic I'm going to talk about is tablet. But before I do that, I want to quickly start a demo that you can run yourself with Instruct. I will share the link to it in the chat. This demo, kind of similar to what Attila did, but Attila actually used full-blown VM. Here I'm just using Docker. So let me first start running 3 nodes of Scylla. As you can see, it's really straightforward. And I'm running a process. I hope the font is big enough. I'm running a process called the node tool status that lets me know what is the status of each node. As you can see, the nodes are almost running. I also have a monitor and dashboard here. I will touch on that later, and a loader tab. So let me actually run a loader so it will be more interesting. Okay, now I started to run a small load on the cluster. And soon I'm going to get back to this demo because I want to demo a new feature that we call tablet. But before that, I need to quickly explain what tablet is so the demo will make sense to you. So until latest releases of Scylla, up to Scylla Open Source 6.0 and up to Scylla Enterprise 2024.2, each table, and Scylla, we didn't cover it, the data modeling part, but Scylla work with tables similar to other databases. Each table data was stretched across all nodes in processes we call vnodes, regardless of the size of the table. And this distribution of the data on all nodes was static. That means that the only thing that determines where each information element will reside, and usually we have 3 replications, is this static algorithm, sometimes called partitioner, which only change when you add or remove nodes from the cluster. But the database itself didn't have much control over that, with the exception of setting the static algorithm at the start. Drivers were also aware of this static algorithm, so they can try to send the request directly to the right node. If they miss, no problem, all the nodes in Scylla symmetric, the node will just route it to the right node, but it's take an extra hop, and we will try to avoid it. One of the big projects that was implemented in Scylla in the last few years is the Raft consensus algorithm, which in turn allows us to implement a global system table that holds the information in a consistent way, which tablet belong to which node. And this basically allows us to make a dynamic decision of which part of a table called tablet belong to which node, and Scylla can dynamically change that. And this have a lot of advantages. Each of these small tablet, it's up to 5 gigabytes or so, but of course, we can play with that. And if each of those have its own log structure, merge tree, its own file on disk, etc. And Scylla can move a tablet dynamically from one node to the other in a consistent way and in a safe way. And this gives us a lot of advantages. The 2 main advantages is better load balancing across a cluster. If Scylla identifies that one node is overloaded or the storage is too high or any other trigger, it can play around and move a node from side to side. Another thing that we can do is when we scale, when we add a node, we can dynamically rebalance very quickly the nodes between the tablet. And this is something that this movie tried. It's not a movie, it's a recording of a simulation that we did. This is a tool that we are using in development to look at tablet, but I also want to actually demonstrate it in Instruct. So what I'm going to do, I'm going to quickly scale out the cluster. This is a cluster that I spawned before. Okay. Oh, sorry, I tried to run it in the wrong tab. Okay. Now it's working, I hope. The loader will continue to work. This is, and let me try to refresh. Just a second. So this is a similar monitoring dashboard to what Attila showed before. The thing is that it's the number of requests per second, of course, is much lower because I'm running everything from this VM. And I just scale a cluster from 3 machines to 6 machines. As you can see, it's changing as we speak. Let me try to scale it. And what I want to do next, I want to move to another dashboard, to the detailed dashboard, and let's see if we can see the tablet in action. Okay, as you can see here, it started. These are two panels that show the tablet status, how many tablets you have per node. And this is a heat map that shows the same thing on the top. As you can see, we started with 3 nodes, and very quickly the Scylla load balancer shift the tablet around to the new node. And the advantage here that the new node very quickly start to serve requests. If in previous version of Scylla, for the node to start serve requests, we have to migrate all the data to him from the other nodes. And only once all the data was migrated and compacted, it start to serve requests from the user. This could take hours before. If you imagine there is in Scylla, we commonly have nodes with 10 terabyte, 20 terabyte, even 50 terabyte. So moving 50 or 40 terabyte from machine to machine take time. It's still take time because we cannot break the law of physics. But the difference here is once we migrate the first tablet, the new node can already start to serve requests. And this is something that we didn't have before. So usually when you need to scale, you don't have all the time in the world because you are scaling because there is some limitation on resources. Otherwise you wouldn't scale. Maybe you forecast a burst or something like that, but in many cases, scaling is very urgent. And with tablet, it's become much, much faster because, again, nodes start to serve data immediately after we added the node, as you can see here. By the way, again, you can run the same demo yourself very easily. And I will leave the link in the comment. Okay, so that was the tablet. One other cool feature that we are adding to Scylla Enterprise only is file-based streaming of tablets. This is like an extension or an add-on, if you will, to the tablet mechanism that allow even faster scaling for enterprise release. We also added a bunch of performance improvement to the latest, and we are doing it with each enterprise release. I'm not going to explain each of this improvement because it's a accumulation of a lot of smaller improvement. But if you used to work with previous version of Scylla, especially Scylla open source, you would find that newer version just work faster, higher throughput, and lower latency on the same hardware. So that can translate to using a less VM, for example, on the cloud. Another cool feature that we are gradually shipping is better compression of network and of storage, by the way, which is not mentioned here. Better compression of networking is crucial, and it's important because two things. First, it's add latency. If you need to just transport more information across between nodes, and usually in Scylla, you locate node in different zones, sometimes in different regions, then you lose performance for that. The second thing, which is as important, is cost. As you know, cloud provider like AWS charge you per cross AZ and cross region byte. And with better compression, you can eliminate it. By the way, the data is also encrypted on transit in most cases, but that's another topic. And the last thing I want to mention that we are taking all of these goodies that I mentioned earlier, like better performance on enterprise, table-based elasticity, and all of that, and bring it to Scylla Cloud. So you can benefit from all of this improvement with a click of a button. So if you go to Scylla Cloud, start a new cluster, very soon, all the action that you're taking on Scylla Cloud, like scaling out, scaling in, or just creating a new cluster will just work much, much faster under the hood, and it will be visible to you. So consistent metadata that we achieve with Raft plus elasticity is much better performance and reduced cost. And just last thing before we are done, a second poll, how long does it take you to scale your existing database? And again, I think a better answer would be how long does it take you to scale per terabyte, because otherwise it's meaningless. But anyway, let's collect the information. And with that, I want to thank Attila for doing the hard part of this presentation. And you guys are more, hi Attila, and you are more than welcome to future events. We have masterclass and the Scylla University live event across the year. And the most important, the Monster Scale Summit coming out in March, and much more about Scylla and Scylla roadmap. So thank you very much. Thanks, everyone. And thanks, Attila. And we can answer a question on the chat. Thank you.
Thank you guys for joining.